Hello, Physics 2 people. In this video, I want to describe the EMF induced or generated by rotating disks and rods in the presence of a magnetic field. This will give us ultimately an example of a homopolar generator, otherwise known as Faraday's disks, which is a real device that can be built. Before we go into that, I want to just kind of focus in on a rotating rod, because if you can understand that, it makes the generator very easy to understand. So here's what I'm imagining. I have a copper pipe or some sort of metal here, which is rotating with some angular velocity in the presence of a magnetic field. And we're going to describe this two ways, once using forces and once using Faraday's law. And again, as always, the motional EMF will be the same as the induced EMF, but it's just a different perspective on it. Okay, so you could do that. So this point right here is going to be fixed. It's going to be the axis of rotation. So it's just rotating around this central point. And okay, so focus in on a little segment here. Let's try to draw that in there. A little segment of length. So that length would be, ds would equal dr, because it's radially oriented away from the axis of rotation. And the velocity of that little segment is perpendicular to it, so you'd have some velocity there. Okay, so now let's use the right-hand rule, and we would see that there would be, so V cross B, you're going to get a force on the positive charges carriers wanting to accumulate at the axis of, at the center of the axis, and a negative charge carrier would want to accumulate at the other end. So we're going to get a magnetic force is going to cause charge separation. It's going to cause an accumulation of positive charges here and negative charges on the other end. But if you get charge separation like that, you're going to have electric fields. And if you do this, and let's say we were running this in let's assume we run this in steady state. So in steady state, we must have then that the electric field generator, the electric field forces must balance against the magnetic forces. And so it must be that the electric field equals, well, we'll worry about magnitudes here. It must equal V cross B, which is just V times B. All right, so I'm working with magnitudes. And now if you think about it, the velocity of this little segment, that must be nothing other than R omega times B. And if we want to describe this in terms of a potential difference across the rod, we would get the energy difference across the rod. So the potential across the rod is going to be minus integral of E dot dr, or dot ds, sorry, which in fact is nothing other than the integral of the electric field. At least if I just focus on the magnitude, I won't worry about the minus signs. That's going to be the integral of omega times B times R dr So this looks like omega b r squared over 2 is the EMF, let's call it, generated across the rod. So the idea is you have a rod, each little segment is moving, each little segment experiences a motional EMF. I called it potential. I really should have said this is adding up. These are motional EMFs. So you add up all the motional EMFs and you're getting the following expression. On the other hand, we could analyze this from the point of view of Faraday's law. So we have this magnetic field. And we have a rod. It's rotating, some angular velocity. And just for right now, let's imagine I'm going to draw on a fictitious starting configuration. So assume at time 0, it's oriented somewhere. It doesn't matter where, but it has to be somewhere. And then you could imagine that there's some angle as a function of time, which equals omega times t. So it's rotating around like that. Now, Faraday's law says that the EMF around the loop, any loop, is minus the time derivative on the magnetic flux. So as the rod rotates around, if we can generate any loop, whether or not the rod is part of it, this is true. So this is true with or without the rod. But if we're smart and we kind of sketch in a region here, and I'm going to kind of trace out the circular arc, then we can apply this to say that the EMF around this loop must be given by the same formula. So let's work out, what is the flux through this sort of pizza slice? Well, that's just given by the fraction of the circle which this swings out, the rod swings out in this time t. So I'm going to say that the magnetic flux is, well, it's going to be pi r squared. That'd be the full circle. And then we only have an angle theta, so we only want the fraction theta over 2 pi. So that's just going to be 1/2 r squared, and remembering that theta equals omega times t. Okay, so that is the magnetic flux, and therefore the EMF generated around that pizza, that wedge. So the EMF is generated around this, must be minus the derivative. And again, I'm not worried about minus signs. The minus signs follow what you would get from Lenz's law. The EMF is going to look like the derivative on the magnetic flux, and that's just going to be 1/2 r squared times b times omega, because I just take a time derivative. Oh, I forgot my magnetic field. Let me put that in there. Sorry. And that's my formula that I get. So okay, so we get the same EMF generated, either using Faraday's law or adding up all the motional EMFs that are induced along the rod. And the other important thing to emphasize is that it wasn't important that the rod be physically anywhere, or sorry, that the EMF version is always true whether or not the rod is present. And the other thing I wanted to emphasize, going back, I chose this fictitious starting line, but I could have also started it here. It wouldn't have mattered because, in fact, all of the change and flux, all of the increase accumulates at the leading edge of the wedge of the arc here, or along the rod, as it were. So wherever we put the reference initial position, it doesn't matter. So it's kind of, we sort of draw this wedge to help us visualize things, but actually, after taking the derivative, it doesn't matter where you actually started. So it doesn't matter if it was greater than or less than 180 degrees. It's only the increase in area per unit time that matters. Okay, so now using this picture, we can talk about a homopolar generator. Which will be a DC generator. Okay, so the picture that we will have is the following. We're going to imagine that we have a magnetic field which is uniform, and I'm going to draw it coming in from the left. And then I'm going to imagine I have a conductive disk, a conducting disk. Like that. Okay, so this is going to be and we're going to mark the center there. And we're going to mark a point B here at the top. There's going to be a little connection there, a little contact at B. And we're going to attach a wire there. And we're going to take this disk and we're going to put it onto a rod, which is conductive, a metal rod. And it's going to rotate. So we'll go ahead and, I don't know, doesn't really matter. We'll put a wire contact here. Okay. And we're going to let this thing rotate, and it doesn't really matter which way. It'll rotate around like that. Excuse me. And probably you can start to see what's going to happen based upon the last example of the rotating rod. All right, so as this happens, what we're going to do is, as the rod rotates, you're going to generate an EMF, which is going to cause a current to flow. So what I'm going to do is I'm going to mark a point here, like this. We'll call that point A. And what we're going to imagine is that there is a surface, and the surface is going to have a couple parts here. So I'll kind of indicate that in blue. The first surface is going to be between the two wires, the leads. And then, then they're kind of hidden back here. Kind of dot them in here. You can't really, it's behind the disk. And then on the other hand, it's going to turn 90 degrees, and it's going to go between points B and points A. Okay, so the total surface is a combination of this sort of rectangle and then this arc, which is bent 90 degrees. So immediately you can see that there is no flux associated with this rectangle. And since there's no magnetic flux, and since there's none and it's not changing, it doesn't contribute to any EMF. On the other hand, there is magnetic flux through this arc. And the curve we're going to follow, maybe I'll draw that in a different color. We'll do the curve in green, I suppose. The curve is going to follow this wire, go down to here, follow the arc from B to A, go back to the center, and then follow the wire on out. So we're going to look at an EMF this way, which is going to amount to a difference in voltage between these 2 points. Right? Well, again, I can use Faraday's law, and I can relate the EMF around this weird loop. I know it's got a bend in it, but that doesn't change Faraday's law. It doesn't have to be in the flat plane. And I can relate the EMF around that loop to the change in flux through the surface. So the EMF is going to be, again, I'm not worried about minus signs. The minus signs will go with Lenz's law. It's going to be related to the time derivative on the flux, but that's really just the same as the flux through the arc. Or through the wedge, sorry, because the rectangle doesn't matter. And that has the same formula as the rotating rod. So we find the following formula for the EMF. And the sign of omega determines the sign of the EMF. So basically, if you spin, if omega is constant, then the EMF is constant. So it's a DC generator. Okay, so that is a DC generator. It's called a homopolar generator. Sometimes it's called a Faraday disk. So I think he was the first one to suggest this. All right, so that's it for this video.